everybody. We'll just give it a minute while people virtually file into the digital seminar room. We still have people coming into the webinar, so please just bear with us while we wait for everybody to join us. Okay, well, I think we might kick off. So we welcome back to the next iteration of the GSQ and UQ webinar series. Today we're going to be hearing from speakers on major structures of the Northwest Minerals Province. But something special for today, we're going to have a guest chair, which is Karen Connors from the University of Queensland. She's the one responsible for this absolutely fantastic lineup of people that you can see on the screen in front of you. We've got Jim Austin, Vladimir David, Damien Keys, Peter Ray, Gordon Lister, Steve Micklethwaite and Pete Betts. So I'm going to hand over in just a moment to Karen, but in the meantime, please, if you have questions, write them in the Q&A function at the bottom of the screen, and we'll endeavour to do that throughout the webinars, and if not, stick around for a chat at the end where we can have a live discussion. And I'll just give a plug for our next webinar, which is a month away on the 29th of April, which will be have an international flavour of critical minerals collaborations, and we'll hear from the Geological Survey of Canada, US Geological Survey, Geoscience Australia and others. But in the meantime, Karen, up to you to lead us through today.
Excellent, thanks Helen. I might rely on you to keep an eye on the chat and questions because you're used to doing that, if that's okay. So I might start, Jim, you're first in line on my screen, so I might start with you because I know you have to finish early, and I'll just hand over you to introduce your talk because I can't recall whether you ended up deciding on Cloncurry fault or deeper structures. Thanks, Jim. Do you want to start sharing? Okay, you're still on mute. Excellent, we're seeing the right screen. Oh, you're still on mute. Oh.
There we go. You got me now?
Excellent. Yes, got you now.
Okay.
Thank you.
Sorry for that. Okay. Yeah, I thought I was going to be in about an hour's time, so it's good to go early though. So I was going to talk about something else completely today, but once I saw the lineup for today, I thought, you know, this is a great opportunity to drag out my PhD work after about 15 years. So today I'm going to talk about the Cloncurry lineament / fault zone / fault. And hopefully I'll convince you that it's a long-lived crustal structure that acted as a major fluid pathway during mineralization.
Jim, do you want to just swap screens?
Oh, okay. Whoops. Okay, is that better?
Perfect.
Let's go. So the Cloncurry lineament is defined by worm data, and people probably haven't heard much about worms for a while, but worms are basically points of maximum gradient in the gravity or magnetic field. If we upward continue gravity or magnetic data, we start to reveal information about deeper crustal levels. And hence, when we worm successively higher upward continued data, we generate a three-dimensional sheet that can give us information about structures from surface to depth. So generally speaking, a worm will mirror the structure that causes it, but about half the depth. And that's sort of like the Barry-Murphy principle. So the main goals of my PhD were to determine the 3D architecture of the Cloncurry lineament using geophysics and geology, to reconstruct the geological history, assess its importance as a fluid pathway, and investigate its relationship with mineralization. So the aims of today, I'm pretty much just going to present some highlights from 3 papers. The first one is looking at the lineament, particularly an analysis of the worm data and also some geophysical modelling. I'm then going to look at the Cloncurry fault zone, which is pretty much a tectonic history of that zone. And then at the end, I'll just touch on the metallogenic significance. Okay, the first paper of my thesis utilised magnetic modelling and worm interpretation to understand the geophysics of the lineament. And that's it there. I can send you a copy if you'd like. This map shows the study area, the Cloncurry lineament, the main sort of cross sections across, which I'll show you in a second. And just note the main lithological units in the area are the Soldier's Cap group, which is in that mustard colour. That's a Samopalitic sequence intruded by numerous doleritic sills, which you can see in purple. Then you've got the Doherty Formation in blue, which is comprised dominantly of calcsilicates. And then all through that area, we've also got the Williams batholith, which is in red. So in terms of what the worm data look like, you're looking at the worm data in 2D now. So I showed it in 3D before. Here, so the map on the left, you're seeing the low-level upward continued worms. And these effectively map just about any surface contrast in the magnetic field. The one on the right shows higher-level upward continued worms, and it essentially traces only the most important regional structures. So the worm data is more or less mapping the boundary between cover sequence 2 Doherty Formation and the cover sequence 3 Soldier's Cap group in the near surface, but it's a bit more, I guess it's rounding, smoothing out that boundary in the higher upward continuation. This says magworm, it's actually the gravity worm here. So what we're seeing here in the low upward continuation, it's pretty much tracking along the Cloncurry fault quite nicely, and then up in the north along the Mount Margaret fault. In contrast to the magnetic worms that sort of more closely map the other side of that boundary. So the high upward continued gravity worms, they exist down to sort of 60 or 30 kilometers up to upward continuation of 60 kilometers, which means it's going down about 30 kilometers. There's a bit of a discontinuation near the Saxby granite here. So that may be just due to the low density granites intruding through there, or it might indicate some relatively blind deeper crustal structures, which I think exist through there. To put it in a sort of a crustal scale context, Cloncurry worm is a major crustal lineament. It extends for over 500 kilometers, and it corresponds to the eastern side of a gravity ridge up in the north and to the western side of a gravity ridge down the south. So just note Cannington down here sits right on the lineament down in this sort of high grade metamorphic area down in the south. And there's numerous copper gold deposits sitting along the lineament, potentially at the intersection with these northwest trending structures. The magnetic modelling. So these magnetic models were constructed from geological mapping that was done along numerous transects in the field, and all the susceptibility values are constrained by data that we collected in the field. So the section more or less shows subvertical structures right through this zone with fairly large variations in magnetic susceptibility. So we've got a series of upright zones of high magnetic susceptibility. Most of these are related to zones of brecciation. You can see the Cloncurry fault over here is basically zero susceptibility. This is just another section a bit further south, but essentially this zone of sort of vertical, highly magnetic breccias and dolerites coupled with a series of non-magnetic faults, such as the Cloncurry fault. This zone is what I refer to as the Cloncurry fault zone. It's typically bounded on the west side by the Cloncurry fault and by the gravity worm, and it's bounded on the east side by the magnetic worm. Okay, so my second paper examined the tectonic history of the Cloncurry fault zone, and although this one isn't referenced very much, I think this is probably the best of the papers. So previous workers had written about some mylonites in this zone. Generally, they were assumed to be early, high temperature, high pressure fabrics, and thought to be related to a major mid-crustal detachment or possibly to thrusting. So we actually collected a whole bunch of samples of these mylonites. And from what I can gather, it's fairly clear that we have sort of ductile, brittle fabrics in some of the 1530 age Saxby granites. So that's the example up the top. We're seeing sort of higher temperature fabrics in some of the 1550 MA granites. And there's also some evidence to suggest that the mylitization is overprinting sodic calcic alteration. So that's that example down the bottom. So it appears that these fabrics are not related to an early mid-crustal detachment. They appear to be related to a transition between inversion and strike-slip tectonics. They post-date the major period of deformation regionally, D2, which makes sense because, you know, we're sitting in a zone that has a ton of felsic magmas which intruded from 1550 to about 15 MA. So they're dominantly about 1550 MA in age, we think. Overall, the mylonites are mapped as being a series of anastomosing north and northwest trending shear zones. They have variable lineations, which indicates, I guess, complex transgressive shear rather than simple shear. They're often truncated against some of these north-northwest trending zones. And these appear to show vertical lineations dominantly, which implies, I guess, normal or reverse movement. And we couldn't really figure out which. Well, I'm pretty sure, again, these zones are mostly reflecting pre-existing sort of basement structures that are generally blind. So this is sort of some of the only instances where we see them in the surface expression. At the outcrop scale now, we're in Fullerton Gorge here. And here we can see the relationship between the mylonites and the folding. And it's very complex, as you can see. But the mylonites appear to be subparallel to and likely localized by the fold limbs. So I just want to dwell on this map for a moment, just so you can take in some of the detail. It's incredibly complex on this scale. And I should point out that Blenky made me mark out all these outcrops with 1 meter grids in chalk. And I spent a week mapping all of these things. And these days, people would do the same thing in 5 minutes with a drone, which makes me very angry. But in any case, our model for the deformation describes a zone of anastomosing shear zones and related folds with variable slip vectors. And this ultimately allows a transition from east-west shortening to north-northwest extension. At some point though, likely as we're getting more towards 1530, fluid pressure prevails. And again, at the local scale, also in Fullerton Gorge, we see here that brecciation and albertization in general is localized by and generally sub-parallel to the mylonite zones. And you know, you can see that this blue zone through here, that's not actually what the breccia looks like. That's just a bit of help from Illustrator. Some of the clasts in this breccia are the size of buses. So there's some pretty serious sort of fluid interaction going on here. But not all breccias are the same. There's actually quite a variety of crazy rocks in this area. So I just want to show you some here. In A, which is up in the top left, we're seeing a transition from a mostly intact red rock altered laminated calc-silicate into a sodic calcic breccia. So that's the laminated calc-silicate. We've got the breccia here. That's actually pretty similar to this rock over here, which is sort of a pristine calcite actinolite marble. C, we're seeing a sodic calcic breccia that's been deformed post-brecciation. D is sort of like a laminated calc-silicate. It's sort of verging on a proto-breccia. It's been kinked in conjunction with quartz iron alteration. E, down the bottom, this is the most common breccia that you see. It contains actinolite, titanite, albite, and magnetite. It's very magnetic, and this is what forms some of the large linear bodies within the Cloncurry fault zone. And the last one down there has a chlorite matrix, so this is generally quite late, and this is likely formed synchronous with the later stages, and probably similar to some of the things we see in the middle of Ernest Henry. Okay, overprinting the Cloncurry fault zone, we have a series of quartz, hematite, and sometimes a bit of goethite or limonite or whatever that is in the middle there, breccias. So these are some of my favourite rocks in my rock collection. They're very non-magnetic, and these breccias occur in relatively late faults, such as the Cloncurry fault zone. So they form zones that are very prominent. So this is sticking 20 meters out of the ground, but it probably has another 40 meters of scree on the side of it. So they're very silicified. They're very linear, and I think that indicates that they're late, and I think they formed as the region transitioned from transgression to strike-slip tectonics. But they show reactivation right through to the Mesozoic, as you can see here, the displacement of this Jurassic Mesa here. The architecture of these faults, I think it's consistent with the sort of a sinistral radial fault system. And that's quite consistent with what we see in deposits such as Ernest Henry, which formed at about the same time. That really the late history of this zone, it's really going to sinistral strike slip. And then eventually we're seeing some extension as well. So just to synthesize all that, we believe that the lineament initially corresponds to a cover sequence 3 normal fault. There's evidence of some D2 reverse faulting and folding, but it's not very well preserved in the Cloncurry fault zone. It's pretty much well preserved in the Soldier's Cap group, which is sitting out to the east, but we don't really see too much of it in the Cloncurry fault zone. And that's really because the Cloncurry fault zone has really seen a lot of action during D3. So D3 is the main period of deformation. Here we're seeing dip slip, strike slip, strain partitioning as the dominant deformation mechanism. This occurred around about 1550, maybe a bit later. And this transitions into a sinistral brittle fault system at about 1530 to maybe 1510 or so. And then sort of post 1500 million years, we're seeing evidence of dilation and vertical shortening. Okay, so my third paper examined the relationship between the lineament and mineralization. I can't go into it too much due to time restrictions, and it would take too long to really explain the techniques used. But if you'd like a copy, just please reach out. It utilised two different techniques. So one is weights of evidence, and the other was autocorrelation. And here we can just see a plot of where deposits sit relative to buffers around this Cloncurry lineament. All I really want to say here is that there does appear to be a direct relationship between the Cloncurry lineament and mineralization. In particular, Cannington is sitting smack bang on the lineament, and I think it's likely that it's localized by the early normal fault rather than, I guess, the later overprinting of that structure. There's a bunch of sort of pyrrhotite dominant gold-rich systems up in the Weatherly Creek area. I wonder here whether the deep crustal structure, therefore, is basically bringing up the sort of reduced styles of mineralization. So we're seeing the sort of pyrrhotite rich systems and the galena rich system down here at Cannington. It's more reduced. And there's a good clustering between the AU-CU systems here and the lineament. In contrast, the sort of magnetite-rich OCG type systems, they're occurring much more distal to the lineament. So sort of 8 kilometers there. So, you know, I think that's telling us something different. If we look at the spatial relationships of the deposits to each other using the autocorrelation method, there's a strong north-northwest control on mineralization at a regional scale, which is basically what you can see in this rose diagram here. As we come down to the finer scales, however, we start to see that there's this sort of northwest trending pattern to the deposits. And I believe, again, these are suggesting these northeast blind structures in the basement. So I kind of danced around that a little bit, but I believe we need to think a lot more about the structure deeper down. I think, you know, if you look at stuff like the Cloncurry fault, that's really obvious. It's really linear. It probably postdates just about everything of consequence. And I think some of these blind structures in the basement are doing a lot more to localize mineralization. And I guess the take-home message is, you know, I think we really need to think a lot more about structures that we can't see. So that's just about it. Big thank you to Tom Blenkinsop. He really whipped me good during my PhD. And I'd just like to thank Predictive Mineral Discovery and all of my colleagues, such as Damo, who's about to talk today. And you can contact me down there.
Excellent. Thanks very much, Jim. Now, I've got one question here in the chat from Rob Hewson saying, great talk, comprehensive geology and geophysics integrated. Just wondering if any of the shallow mag processed worms are related to magmite alluvial or buried paleochannel accumulations? Any typical dendritic worm geometrics to suggest this?
Yeah, well, it's a good question. I don't think so, mainly because we don't really, when we're doing the worming process, we kind of throw out everything under sort of 1 kilometer upward continuation. And I don't think any of this sort of near surface maghemite is really going to do much more than add a bit of noise to the surface. And particularly in an environment like this, I mean, this is really, really magnetic environment. If you're in an environment, you know, like out in the Thompson orogeny or something where it's magnetically very dead, you know, it might influence it there, but I don't think it's doing a great deal here. It does exist though. Yeah.
Okay, thanks. Well, we might move on, but if anybody has any other questions, please just put them in the chat, and Jim can
in
perhaps.
The Q&A.
In the Q&A, not the chat. There we go. In the Q&A, and Jim should have some time to answer.
Karen, there's one more question in the chat.
Oh, sorry, in the chat. I wasn't looking at that. Okay. Ben Johnson, you mentioned mineralization fitting a Riedel model. Is there a preferred orientation that's opening up during the mineralizing event?
Well, yes and no. I think what's happening, and it's not necessarily related to the Riedel, but it's definitely related to sinistral strike slip. I think what's happening is whatever is occurring over the top of these basement structures, that's being reactivated, and it's being reactivated in a variety of ways. So if you look at Ernest Henry, for example, you have this northwest oriented shear zone. Once you start shearing that, you're forming this sort of jog through that whole system. So I don't think there's consistent fault orientations so much as the same kind of kinematics are doing different things locally.